Welcome to Part 4, the concluding segment of our Webinar 2 series, the subject of which has been First Steps to Supplying Legacy Castings. Our Part 4 title is Machining Principles, net shapes that are 80, 90, or 95% as cast. My name is Julia Speaker, and I am the team lead for the American Metal Casting Consortium's Castings Advanced Systems Technology Integration Team, also known as CAST-IT. This seminar is funded by the Defense Logistics Agency and has been developed by the CAST-IT team to assist DLA suppliers in successfully supplying these complex cold start legacy castings. Our target audience is machine shops, who now comprise 70% of DLA's new awardees for legacy casting procurements. More narrowly, machine shops who are undertaking a cold start contract in which they are not the previous supplier, the tooling is unavailable, and the manufacturing engineering details of the previous supplier are unknown. Among those cold start machine shop new awardees, we are reaching out to those who do not regularly machine castings. In Part 2 of this second webinar series, we focused on how and with whom a machine shop could and should choose as business partners in the launch of legacy casting first articles. At minimum, and most importantly, those partners would be a metal caster and a mold cavity tooling builder. Other partners might be a heat treater and a coater. In Part 3, we examined 4 legacy casting case studies in which the dimensional issues resulted in a first article nonconformance or rejection. The 4th of those case studies dealt specifically with the risks and issues undertaken by a cold start new awardee machine shop. This Part 4 is also based on examples. All examples are from a machine shop and fabricator who specializes in machining castings, including current production military castings and including commercial legacy replacement part castings for construction and agricultural equipment. The essence of this machine shop expertise is their understanding of as-cast surfaces. The as-cast surfaces to set up against in the first, and sometimes only machining fixture, the as-cast surfaces to leave alone as net shape, and the as-cast surfaces to upgrade to net shape by machining. Sometimes they achieve final net shape with a combination of machining and adding a net shape feature by fabrication. Guiding us through these machine casting examples is our CAST-IT teammate, Dick Tiano. Dick is our manufacturing expert, including existing and emerging 3D technologies in manufacturing. At the end of Dick's presentation, I will return to open a chat box to field your questions and comments. So I will see you again in a few minutes, and now here is Dick Tiano.
Thank you, Julia. From my perspective in manufacturing processes and new technologies, I want to share with you the first steps in planning for and tooling up for machining of castings. I'm speaking in general and not just for low-volume replacement part castings. On one hand, the choice of machine tool type and multi-axis capability is simpler. On the other hand, the design of fixtures, especially the design of fixture targets that will touch the as-cast surfaces that are already net shape, is much more complex. Instead of fixturing against the consistent surfaces of wrought metal blocks and bars, and forming complex geometry with simultaneous multi-axis pallet and tool movements, castings already have almost all of their final complex net shape. Initial fixturing is against those as-cast surfaces. Compared to wrought metal surfaces, those as-cast surfaces can vary substantially, unless those as-cast surfaces are planned in advance with the mold cavity tooling builder and the metal caster. Planned in advance with the machine shop's manufacturing engineer to have surface consistency where the first and maybe subsequent machining fixtures will touch the casting. The most concise way to convey the uniqueness of machining castings in the contents of first steps is through pictures. I have organized the sequence of pictures on the basis of machine tool type, multi-axis pallet type, and finally, fixture design. First, old school non-CNC machining. Second, CNC machining with one axis. And finally, CNC machining with multi-axis rotating pallet. Now, let's take a look. Our first example is an old school non-CNC drilling of a shoulder bolt clearance hole by means of a heavy-duty drill press. The casting is net shape, 98% as cast. The fixture design is very clever, and it is based on principles of geometric dimensioning and tolerancing. The fixture holds the casting in the same way the casting assembles on the 18-wheeler truck, controlling the pivoting of its hood opening and closing. Cosmetically, a right and left-hand casting controls the gap between the truck's hood and cowling, so dimensional control for alignment is important. The casting is made in the resin shell process, which is the most accurate of sand mold processes. There's a 1 degree draft in the slotted holes checked with a go-no-go gauge. Hole size and position tolerances allow as-cast holes so long as they are actually formed and carefully finished. The design principles of the hydraulic actuated fixture is no wiggling when the fixture clamps the vertical slotted holes and the horizontal slotted hole. If the casting wiggles, it is removed from the fixture, not machined, and returned to the metal caster for salvaging or scrap. 6,000 pairs of these castings were shipped annually with no returns or no complaints from the truck manufacturer. Here is a single-axis horizontal CNC setup for machining a ductile iron sand casting that functions as a cover. The horizontal CNC machine tool has 2 general-purpose tombstone fixtures, clamping the casting on drafted surfaces, which we will talk about in the next slide. The 2 similar fixtures are required to access each side of the cover. This casting is about 65% as cast net shape, which is on the low end of as cast versus machine features. The inset below shows each side of the casting prior to and after machining. Although it's a simple casting, there is an important fixture design consideration to be illustrated here. The casting has a drafted surface around the entire perimeter of its rectangular shape. Normally, it's good practice not to fixture on drafted surfaces. However, if it is done carefully with an understanding of how draft works, setting up on draft can be successful as it is shown here, realizing that the draft is really a combination of an offset and a draw length, like the offset and depth of a cupcake pan. In this case, the draft offset is the same all the way around the casting, so a 3 degree dovetail on the fixture's clamp surface can readily be matched the draft. The important part of fixture design against a draft surface is to clamp the casting at the same offset level wherever the casting's draft is touched. To accomplish that, a go-no-go gauge is used by the machine operator to make sure that the casting's front surface is at the same elevation across both dovetails. The idea is expressed by the green lines along the fixture's dovetail clamping surfaces. Once that no-go gauge is satisfied, the casting can be fully clamped and the holes and the mill surfaces will be orientated correctly to the casting's as-cast datums. This one is an actual DLA legacy casting with its 1977 2D drawing in the background. It is a 1 setup, 1 axis, vertical or horizontal CNC machining example. Shown in the foreground is the first solid model built by the mold cavity tooling builder, which replicates what the drawing calls for exactly. It does not have draft or parting lines or other features of its air-set sand casting process. This first solid model just replicates what's required on the 2D drawing. The casting is 90% as cast in its net shape, and the only machined features are on the top side surface, faced, grooved, drilled, and tapped. Here we see the second solid model with two more views of the 2D drawing in the background. The second solid model has draft added to the perimeter sidewalls, and it has pattern maker's contraction added to all the geometry, making it larger by the contraction rate. It also includes all the process interface geometry, that is, the liquid metal delivery system and the cylindrical risers to feed the solidification shrinkage. You can also see in yellow a core print where a core will fit into the bottom half. Although drawn in 1977, form the handle feature. The 2D drawing does a decent job of defining and implying the as-cast features, which become the datums for the machining setup. Shown at the lower left are the primary, secondary, and tertiary datum targets to assure that the machine features on the top surface are located correctly. The view at the upper right shows how the casting would be clamped in the fixture. The green surfaces are where risers were attached. It is okay to push against those for clamping, but they should never be used for datum targeting because they are hand cut and hand ground to match the casting's molded profile. Too uneven to be used for targeting. The handle feature is used to pull the casting down in the fixture against the three datum A targets. As we saw in the prior ductile iron casting example, the two datum B targets and single datum C target touch the drafted perimeter of the casting's rectangular profile. Once again, it's okay to target on a drafted surface so long as the drafted angle remains the same where targeted and draft offset is touched at the same elevation. Note that B and C datum targets are smaller in diameter to assist in touching the draft surface in the same offset elevation. Here is our first more complex casting geometry. It is a high alloy steel casting made in the ceramic shell investment process. It is machined in two single axis setups, one for a horizontal CNC and the other for a vertical CNC machining center. Like so many other investment castings, it is 97% as cast in final net shape. The accuracy and surface finish of the investment process enables the faces of the drilled and tapped surfaces to remain as cast. Those are shown in pink. At the lower right is an as cast pocket whose size and position tolerances are met by the capability of the investment process. The design of the fixture for the horizontal CNC machining center is shown here. Holes are drilled and tapped on each side of the casting's T-bar in a rotating fixture. Note that the contact of the investment casting's liquid metal delivery tree is avoided in the fixture design. The surface is hand cut and hand ground, therefore too wavy and inconsistent in surface profile to be set up against. Here is the remaining setup on a single axis vertical CNC for drilling and tapping of the remaining hole in the vertical leg of the casting's T-bar feature. The hole is located against two adjoining faces at the end of the vertical leg and clamped with screws on the two opposite faces. Self-locking clamps hold the T-fixture in place against the drilling forces. Note, once again, the investment mold tree connection shown in blue-green oval is avoided in the fixture design. This is an interesting example of a more complex machining in 3 planes, but accomplished with a simple single-axis CNC setup, followed by an innovative multi-axis pallet setup on a horizontal CNC. The images at the upper left are the as-cast surfaces, and those at the lower right are the finished machined part. Despite being machined in 3 planes, the casting's final net shape is still about 80% as cast. The casting is very simple. It is an air-set aluminum casting formed vertically in the mold with no cores. The as-cast geometry at the upper left shows how the mold is parted with the gusset features formed in the lower half, or the drag half of the mold. The casting is gated and risered at the parting line of the mold, on what becomes the dovetail machined feature. The first setup is a single axis vertical milling of the dovetails on the bottom of the casting. The image at the upper left is marked up with one concern for this casting mold design. If the mold were to shift in the direction of the green arrows, then the machine dovetails would be skewed with respect to the casting's proper center line. To mitigate that possibility, the casting is clamped primarily against the vertical face between the side gussets. Then adjustable targets with limiting stops are tightened against the fixed targets on the back side of the casting in the same relative positions. If the adjustable targets with their stops cannot tightly clamp the casting side to side, then the mold is shifted beyond the tolerance limit. In that case, the casting is set aside, not machined, and returned to the foundry. Otherwise, as we will see in the horizontal CNC setups, the casting is set up on its machined dovetails, no longer using as-cast surfaces to control the machined features in the other 2 planes. Now, we can see how the machining of the casting in the other 2 planes is accomplished. Here, we have a setup for the horizontal CNC with a 2-axis pallet with 2 fixtures mounted on it. The fixture at the left rotates the casting to access the face of the vertical feature and the sides of the gusset features. As machining begins, the casting on the rotating fixture has just come off the prior vertical CNC single axis setup that machined the dovetails. As you can see, the machined dovetails are now the setup feature for the completed machining in both fixtures. The casting on the right-hand fixture has come from the drilling and boring accomplished in the rotating fixture. The insets at the lower left show the finished machined casting in its 3 planes of machining. The takeaway from this example is the clever use of a relatively unsophisticated vertical and horizontal CNC machining centers, making a fairly complex finished machine net shape from a simple air-set sand casting with no cores. The casting's net shape remains relatively high at 80% as cast, and the overall cost effectiveness of the manufacturing engineering of this finished casting is excellent. Our next example is a casting made for the same customer as the prior example. This one also has a machined dovetail on the bottom side. However, it is entirely different casting and is molded completely different. Like the prior example, this casting is machined in 3 planes, but only uses 2 fixtures instead of 3. This is done by applying all the axes of the horizontal CNC's multi-axis pallet. Here's an overview of what the casting looks like. The photograph was taken with a wide-angle lens, and the vertical surface at the right-hand side really is at 90 degrees with respect to the bottom. The main point is the casting is hollow all through its center, and the hollow section extends into and through that 90-degree feature at the right. Even though the casting is machined in 3 planes, because it is so hollow, it is still 90% as cast in its finished net shape. The next two images explain how this casting is made better. The image at the left shows how a single core forms all of the hollow features. The image at the right shows how the handle features are molded out rather than cored. Cylindrical features, like these handles, in a plane parallel to their long axis, have a large amount of natural draft and can be molded in sand directly and easily. Here are some as-cast features that are important to the machining of this casting. First, the mold parting line is along the major axis of the casting along its length. Second, you can see riser contacts on the bottom of the features that will become the dovetails. It is important for the foundry to grind those riser contacts down near the adjacent mold surface, but not below it. If a riser contact is underground, the grinding may cause the machine surface to not clean up. On the other hand, if the contact is left too high, especially in alloys that are more difficult to machine, such as steel, a sudden heavy cut may damage the tooling. Third, notice the sand inclusion pit. A judgment has to be made by the metal caster before the casting is shipped to the machine shop, whether or not that sand inclusion pit is deep enough to cause a non-cleanup in the mill surface. In webinar 1, we talked about in-process weld rework. If the sand inclusion were deeper, the metal caster would excavate that pit slightly to be sure that it is clean, and then weld and grind the welded aluminum back to the original molded surface. And then the casting is heat treated to be sure that the casting strength and machinability are uniform. Finally, there's an interesting little cylindrical feature in the right-hand view that provides extra material to form the as-cast exterior profile of a large diameter drilled hole through the side of the casting. Here is a view of the machining of the casting's top features and a view of the right-hand vertical face. Finally, the side with multiple small drilled holes and the large hole that require as-cast cylindrical stock between the dovetail rails. And now, the manufacturing engineering for the machining. This is the first machining setup for a vertical CNC with only one machining axis. This is similar to the first setup on the prior red casting, but this setup has less risk of machining misalignment. The prior red casting was targeted and clamped on molded draft at each end. The required clamping screws that had stops to prevent mold shift that could cause misaligned machining. If the stops prevented a tight clamp, the casting was set aside and not machined. Here, there is no draft issue, and the clamping and targeting is a simple across the width of the casting and along its length. As noted previously, the riser contacts are machined away in the face milling of the dovetail features. Here is the pallet for horizontal machine tool that rotates in two planes. Mounted on the pallet is the fixture that will clamp onto the dovetails machined in the first fixture. In the next slide, we will see how the casting is set up on this fixture and how the pallet rotates to enable the machining of all the features in two additional planes with this single setup. Now we can see how a single setup on the machine dovetails enables all other drilled, tapped, bored, and milled features to be performed through the rotation of the horizontal's CNC pallet. In summary, Machining of castings is a market niche significantly different from the extensive multi-axis machine geometry formed from simple wrought shapes. The distinguishing niche characteristics of machining castings are: a very high percentage of the features are net shape in their as-cast form. Castings have anomalies on their surface features that must be avoided in fixture design. Although draft is an anomaly with respect to the 2D drawing, which typically allows draft but doesn't specify where it shall be, draft can be accommodated in the machining fixture design with careful manufacturing engineering between the mold cavity design and the machining fixture design. Machine tools have many types, may be applicable for the machining of castings, even the old school non-CNC tools. Multi-axis CNC machine tools are important in casting machining for access to machining planes for relatively simple cuts. Collaborative manufacturing engineering of machining fixtures with the mold cavity tooling builder and the metal caster is critical to cost-effective machining success. Now, here's Julia to wrap up with a chat session for your questions and comments.
All right, good morning, everyone, and thank you for joining us for our final part in this First Steps webinar series. As Dick said, my name is Julia, and I'm the Cast It team lead. It looks like most of our attendees have attended either, part 1, 2, or 3, so I'll be quick in my intro here. But I do just want to remind you that we exist to help solve technical and procurement issues regarding castings. So if you ever experience those in your day-to-day work, please reach out to us, and we're happy to see how we can help. In the handout section, there is a couple of handouts that kind of outline the type of work we typically do and a couple of ways we might be able to assist you. So without further ado, I'll go through and introduce our Cast It team. So on the line, we have Dick Tiano, who's an expert in all things 3D data, Mike Gwynn, who is a casting design expert, and Keith Sturgill, who is a metallurgical engineer and an expert really in all things DLA and government processes. So also on the team, but unable to be here today, is Dave Powlite and Gary Burrow. So let's go through and see what questions we have. So it looks like we do have a couple. So I think, Dick, this one will be a good one for you to answer. In the first machining fixture design example, what was the purpose of the no wiggling when the fixture clamped the casting?
Thank you, Julia. Good question. In the webinar 1 series, the concept of a functional gauge was cited as powerful in assuring dimensional compliance, not only for the machining, fixturing, and final assembly, but also for first article dimensional conformance. In short, a functional gauge holds a casting as cast datum and assembly features in a way that verifies correct alignment in a machining fixture or alignment in final assembly. And it also holds the casting for processing purpose, like finish grinding, the parting line, or matching lines. But in this case, there was no operation in the castings finishing process that made sense to build a functional gauge to hold those right and left-hand castings for a process like grinding. However, the machining fixture was ideal for the purpose, so long as the casting was evaluated first in the fixture before the shoulder bolt clearance hole was drilled. So that's a long path to the answer about no wiggling. If the castings as cast 90-degree feature and or either of the as cast slotted holes are not in tolerance for orientation, size, or positioning, then the casting will wiggle as the hydraulics clamp on it. The wiggle is a clear sign that there is a dimensional problem somewhere within the casting. The machine shop simply removes any casting that wiggles and returns it to the foundry. The foundry can then evaluate the cause of the wiggle and either fix it or scrap the casting. And Mike, you may want to add something to that as well.
All right. So Mike, just an FYI, but you were muted, but I think he was saying that your answer was perfect, so. All right, so it looks like there is one more question. Dick, again, I think this one's probably for you. What's the main difference in utilizing the axis movements of a pallet for a casting in a machining center as opposed to axis movements of a pallet in machining a wrought block or a bar?
Another good question, thank you. So imagine machining a large helical gear from a bar of wrought high strength steel. The 3D profile of all the gear teeth would require programming simultaneous movements of the machine tool axes and the pallet axes to accomplish that complex machined 3D profile. As we've seen, a casting is already 3D, and this 3D shape is already 80, 90, or 95% or more in its final net shape. So for machining a casting, the usefulness of a multi-axis pallet is simply to reorientate the casting to put relatively simple machine profiles in it or on it.
All right, great answer, Dick. All right, so it looks like that is all the questions we have. So once again, I just want to thank everyone for participating in our First Steps webinar series. If you missed any of the previous sessions, or if you want to reference back to them or this one, I will be posting the recording of this into the same playlist. I've previously sent out the link if you attended one of the other sessions, but I'll be sending it out again. I think these are great to save for future reference. In addition to that, we do value your feedback. There's going to be a very brief survey that pops up right after I end today's webinar. So we would love it if you could fill this out. We do take any sort of suggestions, critiques, comments. We take those into consideration as we do future webinars. But that is all I have. So once again, thanks everyone, and I hope you guys have a great rest of your day.